Hey gang, welcome back. Happy Wednesday. Today, class number 38. We've got today, Friday, and Monday is the last day of classes for the semester. Hopefully you're working on project number 9. That's going to be due Monday coming up. I have just handed out project number 10, so grab one from your tables. That is going to be due at the start of the final exam, which will be Wednesday, a week from today. Project number 10 is not a math project per se. It's just an opportunity to tell me how the course went for you and to reflect on what you accomplished this semester. All right, it's something that you might want to just kind of bang out today so that you're freed up to, focus on your other assignments and finals and things like that. You'll see here that there is a quiz, but remember I've taken that off the table. I'll hand it to you, but I'm not officially collecting it. If you want to turn it in, I'll give you feedback on how you did. Any questions on the calendar? Okay. So let's go ahead and start on page 70, what do we say, 73? Okay, 73. Today we learn a qualitative technique and a numerical technique for studying the family of solutions of an ordinary differential equation. So we're going to take a look at number 1 here, which is a mixing problem. So I'll read it and then we'll see if we can set up a differential equation. It says at time t equals 0, a tank contains 4 pounds of salt dissolved in 100 gallons of water. So big old tank. And then we've got brine. You guys know this word? Salt water is good. So we've got salt water containing 2 pounds of salt per gallon. Is allowed to enter the tank at a rate of 5 gallons per minute, and then the mixed solution is drained from the tank at the same rate, all right? And so we've got this salt water coming in, and this tank has like a big old, I don't know, like a fan type thing at the bottom that just mixes it all up. And then the mixed solution, the mixed salt water, drains at the same 5 gallons per minute, okay? And so the water level in the tank is staying the same, but what's changing? The salinity, the amount of salt in the tank, right? And so we are going to set up a differential equation that models this. This is a complicated situation. The stuff coming in is easy, it's fixed, but the stuff going out is changing at every instant. Like how salty the water leaving this tank is changes at every moment in time. And I'll say that that this same kind of setup could be applied to, for example, pollutants entering a river. Like maybe there's a factory that wants to set up right alongside a river and they need to get permits and they need to do this kind of analysis to show, hey, yes, we're going to be dumping all kinds of garbage in this river, but the river can process it. Like long term, the river is going to suffer no ill effects. Or, like long term, hey, this is really going to mess up the river. And if the board decides that, then they should say no to the factory, right? You could also imagine like a patient in a hospital with like an IV in their arm and like some kind of like drug given to them like a little bit all the time. And we want to know what's the long-term effect. The body is processing this drug, and how much drug is in the system at every moment changes, and the body will adjust and adapt to try to process the amount of drug in the system. So maybe you don't care about salt water in this tank, but there are tons of applications that are just like this one. This is sort of the standard intro one. Okay, here we go. We are going to let Q of t equal the number of, we're having some problems here with our smartboard, gang. It seems like we are diagnosing a diagonal path. Yeah. All right. So watch how I cleverly avoid writing on that diagonal path. All right, let's try this again. Okay, we're going to let Q of t equal the number of pounds of salt in the tank at t minutes. So for example, how much is Q of 0? I think it's given as a number in this problem. 4 pounds, right? It just tells us initially there's 4 pounds. Okay. All right, and now we are going to try to set up a differential equation here. So we are going to write dq dt. In English, this represents the rate at which the number of pounds of salt in the tank changes as time passes. Rate of change of salt with respect to time. For sure, this is equal to the rate of the salt coming in minus the rate of the salt going out. Agree? Those are the two reasons the amount of salt in the tank changes. If more stuff comes in than goes out, then the water is getting saltier. If more salt goes out than comes in, then the water is getting less salty. Okay, let's start writing some expressions here. The rate at which the salt is coming in is equal to, I'm going to multiply two fractions together here, so check this out. How salty? There's like a density given to us for the water coming in. What is it? 2 pounds of salt per gallon, right? And then what's the rate at which the water is coming in, that salt water is coming in? It's 5 gallons per minute. And if we cancel the units here, the gallons, then we get 10 pounds of salt per minute are coming in. Agree? And if we had thought about the units for dq dt, well, we know there's supposed to be q units over t units. What are the q units? Pounds, and the t units, it's minutes. Okay, so we're getting exactly the right thing. 10 pounds of salt per minute are coming in. That's the rate that the salt is coming in, minus. All right, that worked so well. Let's play the same game over here. We're going to multiply two fractions. Start with the second fraction. What is the rate the water is leaving the tank? It is still 5 gallons per minute. All right, we're discovering. We got another. I didn't realize. I thought it was just that. I was doing a good job of avoiding that diagonal. We got 5 gallons per minute. You know the trash compactor scene in Star Wars? That's kind of how I feel like right now. I'm just like getting smushed gradually. Okay, we got one more fraction here. I know what the units are supposed to be. What are they? Pounds per gallon. It's the same, like I'm still looking for the density. I'm still looking to put a pounds per gallon here because I still want gallons to cancel, leaving me pounds per minute. But the things that I'm supposed to put in this fraction, well, they're hard. For the stuff coming in, it was a consistent density of salt. It was 2 pounds of salt for every gallon of water coming in. But the stuff that's changing, the stuff that's leaving is changing all the time. It is the like mixture, and it's complicated. But what I know is that I'm supposed to put the number of pounds of salt in the tank and divide by the number of gallons in the tank. The number of gallons in the tank is given. What is it? It's 100. I'm going to put the entire amount of salt that's in the tank in that numerator. I gave it a name. What did I let equal the number of pounds of salt in the entire tank? Q of t. So I'm just going to write Q in the rest of this, but I'll put Q of t right now just to highlight that it is changing as time passes. Well, that's it. And for both of these things on either side of that subtraction symbol, it's a density of salt times the rate the water is moving. And we've just dealt with the complicated piece right here. The density of the salt going out, it's changing, it's complicated. It's got Q in it, but that's okay. It's Q over 100. Okay, we'll clean this up just a little bit. So what do we say here? We got 10 there. minus 5 over 100 reduces to q, I'll write it this way, 1/20th of q. So dq dt is 10 minus 1/20th of q. Buy it? Okay, so that is the differential equation. If we were to try to solve that differential equation using the technique from last class, remember that means getting all the y's on the side with the dy and all the x's with the dx. In this case, it's all the q's on the left and the t's, which there aren't any on the right. It's complicated. You can't add a 20th of q. Adding and subtracting is bad news. What you'd have to do if you really wanted to, I'm going to put this in blue. You don't need to write this. You could take both sides. You can move the dt to the right-hand side and then divide both sides by this entire 10 minus 1/20th of q. That's the only way to get all the q's on the left with multiplication and division and all the t's on the right, and there aren't any. And then you could solve this one. We're not going to, but this one is separable. Okay, so I think we're good there. Number 2, we'd like to be able to find the limiting value for the amount of salt in the tank as time passes. And again, if this is the river, what's the long-term effect of putting these pollutants in the river? Is it going to destroy the ecosystem, or can the river process the pollutants fast enough that it's really going to have a negligible impact? So we could solve that differential equation analytically using this separation of variables technique. Instead, we're going to use something called a direction field or a slope field. Number 3, this entails drawing little tangent lines at the appropriate slope at a bunch of different points. Let's try. So the last column here is the differential equation we just created. Agree? dq dt equals 10 minus 1/20th of q. And then I've got various values of t and q. So let's just try a few of these here. If t is 0 and q is 100, I'm just kind of making these up. T is 0 and q is 100. How much is this calculation here? dq dt is equal to 10 minus 1/20th of q, which I've somewhat arbitrarily decided is 100 in this case. So what do we get? That's 5. Now what that means is that if t is 0 and q is 100, then the derivative dq dt is 5. So if I'm imagining the graph of q, like maybe this is the graph of y equals, don't draw this. Maybe this is the graph of y equals q of t. What have we just discovered is true at the point 0, 100? The slope right there is supposed to be 5, right? Okay, so apparently that wasn't my graph, but if it were, I'd need to draw something whose slope is 5. So maybe it does something like that, where just at that one purple point, the slope is 5, okay? All right, so I don't know what the graph looks like yet, but if I draw a bunch of these little slopes, I'm gonna get a good sense of what that graph looks like. So at the point 0, 100, which is this purple point right here, I want you to draw a little line segment. The slope is 5. We're just imagining a little tiny part of the tangent line. And if you're zoomed way in, that's pretty much what the curve looks like right there. It's a line whose slope is 5. What if I plug in t equals 50 and q equals 100? What do we get? Don't we get 5 again? Because there's no t's on the right-hand side, so it's still the same 100 for q. So this is a 5, and this is a 5, and this is a 5. So let's go to those 3 brand new points, 50, 100, and draw a tangent line, a little line whose slope is 5. So just draw it parallel to that one over there. Okay, so pretty much any place where the q is 100, we've got the slope of 5. All right, let's take a look at the next one. Here, q is 150. I've left the t blank because we've decided it doesn't matter. If you plug in 150 there, 10 minus 20th of 150. 2.5, right? So you're going to go to any place where the Q is 150 and put a slope of 2.5. My first point is going to be this purple one right here. 2.5 is less than the 5. So you're going to draw something steeper or flatter? Flatter. So you draw something flatter. And I'll just draw the same 4 kind of spots that I drew before. Okay, if we plug in 200, yeah, it's 10 minus 10, that's a 0. So what kind of line? Horizontal. So at every place where we're at 200, draw a little horizontal line. Okay, we'll go to 250. What do we get there? Negative 2.5 is good. So remember the red ones were 2.5. So you're going to draw something just like the red, except what? Just opposite, downhill. Okay, and then one more. 300. Negative 5 is good. Which is the same as which color? It's blue, so steep but downhill. Okay. And so the idea here is that we can draw proximate curves for the value of salt, for the Q function. Let's go ahead and start, for example, at 0, 100, which looks like the origin here. At that spot right there, am I increasing or decreasing? Increasing. In fact, you're increasing by 5. Every minute gets 5 more pounds of salt at that one moment in time. So you're going to increase, but you know that by the time you get to red, you're still increasing, but not as much. Yes? So are you going to be increasing concave up or increasing concave down? Increasing concave down. And so you draw something that's kind of increasing concave down, kind of trying to hit these guys, hit these things, and sort of imagine tangent lines increasing less and less and less. And so that is like one potential salt curve. I said that's one potential one. If you were to start up here at the 150, are you increasing or decreasing? Increasing, concave up or down, concave down. But you're not increasing as fast out of the gate, right? You're only increasing by 2.5 pounds of salt every minute. And so this guy is going to increase slower, slower, slower. Turns out that these curves never intersect each other. Never intersect each other. What if you were to start at 300? Increasing or decreasing? Decreasing. Concave up or down? Concave up. And so you just kind of draw another one of these guys up here, leveling off at that 200. As it gets close to 200, it gets really, really flat, hardly changing at all. And so what this says is that, let's see here, as time passes, that's this horizontal axis, what is the limiting value for the number of pounds of salt in the tank? It's 200. Long term, if you just let a lot of time pass, we're going to get really, really close to 200 pounds of salt in the tank. Here it is, long-term behavior. 200 pounds of salt in the tank. in our case, how much salt did we start with? 4 pounds. And so we're like way below what this graph paper says, but we're going to increase really fast in the beginning and then slow down, slow down, slow down, and level off at that 200. What does it mean if you start with 300 pounds of salt in the tank? How could it possibly be decreasing? Yeah, if we had the salt water coming in and the density of the salt was, what was it? 2 pounds per gallon. If the water that's already in the tank is incredibly salty, saltier than 2 pounds per gallon, then more salt is going to leave than comes in. And so, yeah, it's going to, the amount of salt is actually going to decrease. Salt water is coming in, but it's not as salty as what's already in the tank. Yes, I think that's good. What if it happened that you started with exactly 200 pounds of salt in the tank? Nothing will happen because the 200 pounds of salt in the tank is exactly the same saltiness as the stuff coming in. So the stuff is going to come in, get mixed up with other stuff that looks exactly the same and leave, and it's all going to be exactly the same.
Is that the only way theoretically at least that
Yeah. In theory, we never get to exactly 200. We'll get as close as you could imagine, but never exactly there. So I know this is about salt in a tank, and maybe that's not the most exciting thing. For me, I see other contexts here just looking at this picture. For example, imagine a skydiver. Time is here on the horizontal. Velocity, let's not say velocity, we'll say speed. Let's say miles per hour is here. And so if you are a skydiver, is it the case that your speed continues to increase until you pull that parachute? No, what happens? Terminal velocity, right? Like at some point, your speed levels off. That's where the force of gravity is exactly balanced by the air pressure, force of air, the wind resistance that you create. And that speed is called terminal velocity. Do you see it here? So probably we're starting down here at 0, 0. You just fall out of the plane, and then you speed up very quickly in the beginning, but then your speed levels off. In this case, 200 miles an hour is terminal velocity. I don't know what actual terminal velocity is. What context would this 300, like this 300 would suggest that you actually slow down. The moment you leave the plane, you slow down. If you are fired out of that plane, like there's a cannon shooting straight down out of that plane, and you're unfortunate enough to be in that cannon going 300 miles per hour, well, you're going too fast, right? And wind resistance is going to do better than gravity in the beginning, and it's going to literally slow you down, should you be lucky enough to still be alive, slow you down until you get to that same 200 miles per hour, all right? So not just salt, terminal velocity, plenty of other stuff too. Okay, this 200, by the way, is called the equilibrium solution. 200 pounds. Equilibrium just means everything stays the same, right? If you start at 200 pounds, and at every moment in time, you are at 200 pounds. Okay, so I think that is good there. All right, number 6. Slope fields are handy for studying the overall qualitative behavior of solutions. They're not as good at answering more specific questions like how much salt will be in the tank after 10 minutes. We can't answer that question right now. We answered increasing, decreasing. We answered concave up or down. We answered long-term behavior, but we didn't have any specific information like how many pounds of salt will be in the tank after 10 minutes, or even how many pounds of salt will be in the tank 1 second after we start this experiment. We don't have like any exact data, not from our slope field. But there is a numerical technique. It's called Euler's method, named for the same Euler that we've seen many times this semester, which gives us a very precise way to draw a particular solution by, quote, following the slope field. So there's a picture here that I'm not going to fill in all of these blanks for, But I'll say the idea is we've got this curve. Maybe I'll draw it here in blue just to make it stand out. So we've got this curve, and we've got some starting point. And what we are really interested in knowing is the coordinates of this ending point. But the bad news is we don't actually have the formula for the curve. All we have is the slope field, the kind of thing that we just calculated. And we are going to take advantage of the fact that, okay, well, hey, like finding equations of lines is really easy. And then finding the coordinates of a point on that line are really easy. And what do you notice about this point that's easy to find and this point that maybe is impossible to find? Well, they're not that far apart as long as you haven't moved very much from the original point, right? Basically, just the tangent line is close to the curve as long as you don't move very far left or right. So Euler's method very concretely figures out like how to approximate this point by calculating that point. So the plan was originally to fill in all these blanks together. I'm honestly going to skip that right now and just ask you to move on to the activity. You're going to do Euler's method. The formula is going to be given to you in a table that you'll just fill in. If you want to know really what's going on in this picture, just see me outside of class. I'd be happy to share it with you. But at its heart, I want you to be able to do the calculation, and you'll do that in the activity. All right? So go ahead and start in the activity, and I will walk around.